Good morning, everybody. I would say, I hope that you are enjoying the 6 weeks before, and now we are moving to week 7. And because of the sake of time, we don't have a lot of remaining weeks in our agenda. We have only I would say 7 to 12. I decided to change a little bit the content and moving to more, it's not more serious, but more research focused topics. So rather than making the things easy or academic oriented, let's move to the sixth, the research side. And we'll come now to see week 7 of the artificial intelligence research and creative activities clinic. As I said, during the first 6 weeks, we built the foundation. So we learned how to use AI responsibly, how to work with Python, how to work in GitHub, Copilot, how to, if I can say, how to read AI generated code, how to clean data. And in week 7, we moved into research. In week 7, we will move to research, analysis. Already we started this in week 6. So we started analyzing the data. We started doing basic research because this, if I can say, these weeks or these lectures are not only designed for experts, for faculty, they are also designed for students, and maybe they will need beginner move or beginner push to help them. But for the experts also, they can if they don't need the basic steps, they can move to the more advanced research from this, starting from this week. Today we will work with simulation and experimental design. This example I already worked before a few years ago, but I would say rerun it for Chicago State University. I take it as an example to help people also understand because they are living there. But in our case, it's not real data; it's synthetic data. But I take this. The name of the university is not the name, but the environment, the university environment, to maybe one day they will use it in real scenario, and they will help. It will help them. But it's already, I would say, in archive. In archive a long time ago, and it was digital twin for the environment and the energy. So we can start. We are now. Let's say, as a recap, in week 6, the data set already existed. We inspected it, analyzed it, visualized it, and try to understand the relationship inside using correlation, using the mathematical correlation. Today we reserve that process. We decide to decide which variable exists, how they are interact, what noise is introduced, what features can occur, and which intervention we want to test. This gives something very powerful. We know the hidden ground truth because we created the simulated world ourselves. Before, I just want to say one word here about the digital twin. Digital twin is not simulation based software or something like that. It's replicated 100% the real world. So if we test something in digital twin, when we move to the real world, we will have the same thing. So we have interaction. We have the sensors, and we have the actioner that we can test our algorithms in real world with less money. So let's say, for example, a code in Python or in MATLAB, it is inside the computer, and it created these sensors similar to the real environment and actioners similar to the environment. So we can produce the sensors values, and we will have the actioners, and this is what we call the digital twin. So digital twin, it's the real they have, if let's say, if we have an AI that it's similar to myself. So when you ask me a question and you ask the same question to my digital twin, you will have the same reply if my digital twin is 100%, is how to say, well designed, if we can say like that. So but it's this also this week also, and in all weeks we should say we need this week also. It will give us additional responsibilities. If our assumptions are wrong, the simulation may be work perfectly and still produce scientifically meaningful less conclusions. So I like this sentence very much. A simulator is essentially an argument written in code. So this is very, I like this saying. So what I propose here, to make everything concrete, we are not going to discuss the simulation only theoretically. We created one research system that we will continue developing during the advanced weeks, if how to say, I will see that it will help people to move forward in the real world. But also we can change based on how to say, it's not my judgments, but my own thinking, how we can give the better information to people, and how we can help people in the best way. So we are not here only give codes or only teaching or make people learning lessons from our hearts. We want really to help people to move forward and to develop their algorithms, and maybe it will be good things, good remember for us. So our simulated, I would say, the data that we are using here is completely synthetic. It does not represent actual Chicago University building, students, employer, or facilities. I just created. As I said, it was another research field or topic that I worked before. Now I want only to I move it to Chicago University. In reality there is no relationship with Chicago University, and if someone replicate the same code, it will not work. If we want to replicate it later on for real Chicago University, we need the real values, we need the real parameters, and maybe someone wants to work on this research area, he can do the same, and only change the parameters and by the real parameters in our digital twin model, and it will provide him the how to say, in that time maybe it will how to say, represent the Chicago University. So our simulated research environment contains 4 buildings, 5 zones in every building, 30 days of operation, and measurement every 15 minutes. So this is the conditions that we set up that gives us 57,000 observations. Inside the environment, we can study the occupancy, CO2, particulate matters, temperature, humidity, energy consumption, ventilation, sensor, quality, and comfort. Then we can ask the research questions such as what's happened if ventilation is increased? What's happened if filter degrades? What's happened when a sensor starts drifting? That is what make the example much closer to real research projects. So before writing the code, we need a research question. Our main research question is, can an increased ventilation intervention reduce simulated CO2 exceedance while maintaining acceptance or acceptable energy consumption? So the goal is not only to, because if we have a building that has 20 people, and we want to reduce the CO2 generated by these people, we increase the ventilation. This is easy task and straightforward task. But let's how to say, reduce this CO2 and also by increasing the ventilation, but also less energy consumption. This is the goal. When I was working in that field before, I automated the system in digital twin and in real world. But how to say, I suggest to move, I would say, we move all our research works to digital twin, as it's less, I would say, reduce the money that we are spending for the real instruments, and we cannot, how to say, we cannot buy everything. But in digital twin, if we are I am specialist, for example, for one field, and another one is specialist for another field, we can the university cannot spend the two projects and the money for two projects for these two fields. But it can provide I would say one system digital twin that for both, that with different fields. So we have two digital twins that they represent the real fields, and they can test their algorithms. So this is the idea. So from this question, we define the hypothesis. We expect higher occupancy to increase CO2. We expect higher ventilation to decrease CO2, but increasing ventilation should also increase the energy consumption. Therefore, there is trade-off. Our measurable outcomes include how often CO2 exceeds 1 part per million or 1 ppm, the mean and the peak CO2 values, energy consumption, and the comfort score. This is important research habit. Define the question, hypothesizes, and measurable outcomes before looking to add the results. So the results is the last. So before talking about the results, we need the question first, to the research question and the research gap that we will have. Then how we organize our, so here we have control confronted, I would say, parameters. Maybe they are dependent, maybe they are independent. So we need to organize those variables in best way. The independent variables variable is a variable we can manipulate here. That is mainly a ventilation rate or the ventilation boosts. The dependent variables in our system are the variables we observe as outcomes. So CO2 exceedance, energy use, and the comfort. So We also have the variables that that also we need to use in the control, such as built-in zones, random seed. These are also variables that comes to our I would say our system. The advantage of this, I would say, before talking about the advantage, I think this with these factors, I need to say something about this. Factors such as the occupancy, the outdoor environment condition that influence the system, because also the system is not dependent. This whole system is inside an environment that is more, how to say, more it's related to other system outdoor, so it's not an independent system. So this is the system map. The diagram that we are seeing here summarizes the logic of our system. Occupancy influences CO2. As the occupancy increases, CO2 tends to increase. So the ventilation here, we have also the ventilation works in the opposite direction. So the ventilation, when the CO2 increases, decreases the ventilation, I would say, increases the ventilation, also increases, this is the what we call increasing the ventilation, reduce the simulated CO2. This is not when the CO2 increases, the ventilation increases. When we are saying that like that, it's not real, because we are capturing the CO2. The CO2, if the CO2, we don't have the CO2, so the I would say the ventilation reduces the simulated CO2. So we are measuring only the CO2. We're not talking about the electricity consumed by the ventilation. So the outdoor PM 2.5 influence, the outdoor also PM 2.5, while the filter efficiency determines how much of that pollution reaches the indoor environment. So also we have the comfort. When the comfort also it's a parameters that we need to take care, because it's only taking the, how to say, the system as a robot system or as automated system without taking the user of the system inside our system, which is the human. It's useless. All what we are doing is to make this human, how to say, happy, or in the comfort way, that breathing less CO2 or O2, oxygen, good oxygen, and without, how to say, make their comfort in risk. So don't, how to say, make a lot of, how to say, reduce the ventilation or something like that. So this is the system that it's not, how to say, it's a system that we need to take everything together, and doesn't mean that if we want now, let's, how to say, take this assumption. I want to reduce as much as possible the energy, so I will only switch off the ventilation, and that's it. But it will not make the people happy. The CO2, it will be more in this room. So what I want to do, also increasing the ventilation, it will make these people happy, very happy, because only they will have fresh oxygen always. But sometimes we don't need to make this ventilation always on. Also the building owner, or the university in this case, it will not be happy, because we are consuming more energy. This is the idea. So here I would say, we need to also take care about the sensors. We have the noise, we have the drift, we have the fault, maybe sensor is not working. Maybe these are also influence the humidity, the temperature, and also these are also how to say very helpful, because if now the humidity, the system is very humid, the environment is very humid, it will influence the automatically the ventilation cycle. So it is also important, and all these parameters are important. So this is the important distinction here. The real data are measurements collected from the real world. The synthetic data are artificially generated data that may be or may statistically resemble something. Simulation goes further. So here, when we talk about simulation, simulation contains mechanics and relationships. Data are generated as the consequence of those mechanisms. So that is what we are doing here. So it's not generating data or generating synthetic data. So we are the major advantage that is that we know the ground truth. For example, we know the real simulated CO2 before adding the sensor noise or drift. That allows us to test whether our analysis method and can recover the truth. But the limitation is equally important. Simulation alone cannot tell us whether those mechanisms are accurately represent the real building. This is also very important. So now we move to the on how to say level or deeper technically. These are examples of mathematical relationship that implement implemented in our simulator. For CO2, we start from outdoor baseline and added the contribution related to the occupancy. As occupancy increases, CO2 increases. As ventilation increases, that contribution decreases. So for the PM 2.5, the outdoor contains concentrations enters the indoor environment according to the filtration efficiency and infiltration. Then we have the second layer. The simulator first calculate the latent or hidden true physical value. That after that we generate an observed sensor reading by adding the drift measurement noise and sometimes missing data caused by the sensor fault. This separation between the true states and the observed states is extremely useful for research, because we can deliberately study the sensor error. And all these coefficients are illustrative simulation assumption. They are not calibrated measurement from the real CSU building. So here we can see the simulation examples, how we generate this data, how this, for example, here we have a missing measurement that it represents the real measurements. Here we have the occupancy, the CO2. It's true that both of them are not identical, but it's, I would say, logic that if the occupancy increases, the CO2 increase. But here we have the occupancy is always, how to say, there is no nonce. Here we have nonce, so means that we have some real non-measurement values, it's also help us to, because it's in the real world we don't have always the measurement, the here we can say we lose the measurements, but it comes back and then we lose it, but it helps us. This is what's happening in the real world. So we can have it here continuous and without any noise, but this doesn't represent the real system. And here we have the energy that we how to say we consumption based on the ventilation. This is the parameters that we that we have. So the data that we generated is 15, I would say, as I said, 15 minutes using laptop friendly, no GPU needed, and I will show you later on. It's only how to say, we need simple laptop to run it as always. So no need to have a GPU or something like that. Now we create our actual experiments. We have two scenarios. The first is our baseline. There is no intervention, and the ventilation multiplier remains 1. And so this is the baseline that we will. There is no intervention, means that always the ventilation is on. The second scenario is the intervention scenario. During the periods higher occupancy, we increase the ventilation by a factor of 1.8. An important for an important design principle is that everything else remains the same. So we have we are comparing to simulate the words that are identical except the intervention that we want to study. Another useful aspect aspect of the architecture is that the experiments is defined as a configuration file. We can change the experimental conditions without rewriting the simulation code. So here it's true that I didn't, how to say, use the exact research topic, because if we provide the research topic that I worked before, or I replicate the paper here, it will create more, how to say, ambiguity. So this is why I started with the simple how to say, baseline and ventilation boost scenarios. Then we applied how to say, the Monte Carlo experiments with random seeds. So we ran the Monte Carlo, helps us to I would say to run the simulation many times using the same condition and see. It's not chaos system. We are not studying chaos system, but it's Monte Carlo. We need to go, if we want to go for research, we can research side. We need to increase n. It's not only 100. 100 is too small runs, but we can also, we need to increase it to at least 2000 or something like that. It depends on the case that we are using. If we run the simulation only once, the results may depend too much to one random realization. So instead instead we repeat the experiment here. We are using this, I would say, technique, Monte Carlo runs for the baseline and 100 for the intervention. Because the baseline doesn't change, it's always, we have 1 in the ventilation, so no need to run it with Monte Carlo repetition. No need to repeat it. So we need only once. For every repetition, the baseline and the intervention use the same random seed. The random seed is the parameter that it helps us to make things, I would say, reproducible. So if we use here, I use 2026 as a seed. If all of us, we use the same code using 2026, all of us, we will have the same what we say, the same results. So this means that the experiments are experienced the same simulated occupancy and the environment condition, while the intervention itself is what changes that allow us to estimate the effect with much less random ventilation. But there is an important warning I need to mention it here. These intervals describe uncertainty across our simulation runs. So they are not confidence interval for the real world. This is very important to mention it. So the distinction is verification doesn't mean validation. So we need to distinguish is the probability the most important scientific concept in today's presentation. So if we can distinguish between the verification and the validation in this week and take this as output of our lecture, it will be, I would say, the most important scientific concept of this week. Verification asks the following question: did we correctly implement the simulator that we attended to build? This is the verification. So, for example, I will try to give a concrete example. Does increase in occupancy actually increases CO2? Does increase in ventilation decreases CO2? Are the ventilation within the expected ranges? Can we reproduce the experiments? We can't answer those questions today. So this is how verification asks the question. But validation asks something different. Does this simulator correctly represent the reality? This is the validation. So we can verify the system, but we cannot validate it. If the system is validated, it's 100%, I would say, verified. The answer of that question, we would need the measurements from the real system and compare them against the simulation, because today's data are completely synthetic. So it's completely we can only go to the last point of the verification. We cannot go to the validation, except we will have the real measurement and how to say, input them to our system and regenerate the synthetic data. Then we can have the same verification. So we can say that the system is validated. So the verification and the validation should never be used as if they mean the same thing. So this is very important point that we need to insist about it. The verification cannot, how to say, implies validation, but the inverse is correct. If we have a validated system, so means that we test this system in the real world. We have our digital twin, we have our real data, we generate the synthetic data based on the real measurement, then we test the system and we verify it, then we can say the system is validated. Now, I want to show how we set up the system. So now the actual project, I would say, structure, what we will have in GitHub. You will have this how to say, that I created, so that I would say only fork myself, but always I suggest people to fork and to fork the maximum and give stars to maximum each other. So it will help increasing the, how to say, the, it doesn't mean that, for example, let's take maybe a good repository for Professor Kim or Professor Musa is here. But if we don't fork it and we don't give stars, the work itself is good, but is not apparent. So we need to fork. Is not only publish or I will put this. I already put them in GitHub. If the people doesn't use this, means that the repository is not useful. But it's in reality it is how to say, it gives good foundation for people that they want to start working in research, even though they don't know how to use these files. Sorry. Uh, so the configuration that files contains our assumptions and experiment scenario. We have the simulation engine under SRC source. So this is the simulator that we will run. It depends on all of this. It depends on all of this, the other files. I already do that in, I would say, generated using AI Copilot, and also verified. So this is what we call it. We call it the verification after the Copilot. So because I worked before in this field, I know the values, I know the parameters. Why I'm saying like that, if you want to move to other topic, you need to know this topic that you are working on. So you will be the responsible for that. So then we have the data, the table, the figures, the logs, and the tests. The important point is that the research questions, simulation, assumption, code, and the output are separated and organized. Normally, we could execute this online. But to save the time, I can run it now. But to be honest, if we start from scratch now, it will take time, because we need to create. As I didn't ask I to create, I would say, all this as together, because it's not how practical. We need to create part by part to finalize all. But we can do a demo here if one day, or we can do one demo just or occupy one session just to create the full projects. One project, we take only one project and we create from scratch together. If it will be useful. So the run of the code itself, it doesn't take time. It's 1 minute of only we open the Visual Studio, and then we can run it. But the creation of these files, it takes time. So this is how to say the video that always we need to. This is just a demo video that we run and what we have. I will show you later on the figures that we have. They are, I would say, all the I don't know here to how to, yeah. Here the simulation is done. So as you can see, I run it in this laptop. It's only simple laptop. All the results are saved in the results figures, and the how to say, the tables. We have everything. So if we want to go, we need to go to the results here and see the figures that was generated by this code. So here we have the air quality, energy trade-off, I'll say mean energy and CO2. Here we have the figures that I showed before. Here we have I would say the causal relationship. I will explain this. I'm passing quickly this video, but I will try to explain them. How to say, just is an explanation, but you can't always ask the AI to explain. Same AI here, we need to ask the same AI describe, for example, or what this code is doing, or what's, as we already know in other sessions, the previous sessions. So I will move forward. So the generated how to say results. So for the baseline, we have 57 600 records. We have 2,880 time steps across 20 zones with the fixed random seed 2026 if someone wants to reproduce. We also intentionally simulated the sensor problem, so we do that by ourselves. So approximately 81%, 0.81%, less than 1% of the observed sensors value are missing. So we did that in purpose to simulate the real values. And the system generated 910 sensor faults. Another useful element of the data set is the latent ground truth variables. And normally we with the real sensor, we only work what the sensor reports. So this is what's happening in the reality. Here we know both the hidden simulated truth and what's the noisy sensor recorded. That allows us to investigate the difference between physical states and the measurement. So this is also one, how to say, good of the digital twin, that always we can introduce our thinking inside, even though it doesn't exist in reality, just to see what's happening. And also we have the access to both to all the sensors and all the actioners, that it will give us the how to say better understanding of the system itself. So the CSV file, you can find the data set, and the data set that we generated. So it's synthetic, as I said. It was for another topic. I only moved to Chicago State University by changing some parameters, and if someone wants to replicate and to make it real and in reality, I believe it's not very difficult, as he will have the values, the real values of the system. So this is the figures that we saw before. This is how to say, when the simulation of the element passes our check, we compare the normal ventilation against the occupancy triggered ventilation boost. We repeat both condition 100 times. This is what we are seeing here, and for each pair, the baseline and the intervention experience the same random environmental condition. Then we calculate the difference between them. The output gives us effects on CO2 exceedance, average CO2, peak of the CO2, and the energy consumption and the comfort. We are no longer simply generating the data. We are now using the simulated data as a controlled experimental laboratory. Here you can see the results. So in the terminal that we have, so it's only the average, I would say, the average CO2 also decreases, and at the same time the energy consumption increases. Comfort improves the particular simulation because the benefits from the reduced CO2 overweight some of other modeled penalties. So the interesting result is not simply that one variable improves, but also we have the trade-off between the indoor air quality and the energy. And this is exactly why simulation can be useful. We can study multiple consequences of the same intervention before ever considering real experiments. But again, these numbers describe our model. There is no measurement from the real campus. Here we have the sensitivity. So let's say now it comes how to say comes another very important research step. Even if our results look strong, we need to ask how dependent the conclusion on the assumption that we select. This sensitivity analyze challenges the important simulation parameters one at the time. The tornado plots. So let's I would say move to the other. It's not because here we have only the peaks. I would say the when we can see the baseline, always the comfort is better and the energy. But the energy is more here. Here we have the same similar. When the comfort increase, the energy increase. But the most important thing that when we use the system, so it reduces the CO2 and it's also boosts the reduce the ventilation. This is very important, and it's always good to because we cannot, I would say, sacrifice. Here we are sacrificing the energy with the comfort of the people because the comfort is more important than the energy because in reality we want to reduce the energy but without touching the comfort of the people. Here we have the sensitivity tornado, which I would say always also we need to have how to say. Let me explain a little bit this example. So the sensitivity analyzes, I would say the challenge, as I said, the changes of the I would say the important simulation parameters at one time. But this tornado plot shows that which assumption influence the here which assumption influence the I would say the system. Here this is the heat map. The heat map that provide us the what we call it also the future the filler map. The combination, it shows the combination of the assumption where the benefits and the intervention becomes smaller or can almost disappear. This is important because the good simulation study does not only show where the proposed idea works. So we need always to show the limitation because without limitation in research, the research will stop. If I say that my model works 100%, so I will stop people to work on this topic, but it's not true. Nothing is perfect in the world. So always in the papers or in the discussion session, we need to show the limitation of the people, the models or the method that we are proposing, and then also propose some future works because you are the expert. Propose the future works, and based on people will use your limitation and your future works, and they will cite you, and you will how to say you will have more how to say your work as if you are giving the credibility of the work by saying by proposing by showing the limitation of the model and the future work. This is very important. So it's not always the good thing that my system is the best and 100% correct, which is not the truth. Never ever. How to say we have one system is always true or always accurate. So there is if we have this, so there is no research. So what we can how to say climb, or we actually can climb, we should not say ventilation works. We should how to say we certainly should not say this is will improve the real CSU buildings, and we cannot say that the simulation proves a real world causal relationship. What we can say is much more precise under the documented assumption of this synthetic digital twin, the occupancy triggered ventilation intervention reduced simulate the CO2 exceedance. It also increases the energy consumption, and the size of the effect depends on some of our assumptions. So that is the scientifically, I would say, if we can say that, it's defensible statement. So as I said, a good research is not about making the strongest claim. It's about making the strongest claim that the evidence actually supports. This is very important. So uh, we need to be honest also always with ourselves. We need to say the weakness of the model and the good of the model, and how our model is improving, because all this research that we are doing is to help people and to help the community how to live better in all research fields, from the medicine to AI to computer science to robotics and to arts to mathematics to all every I would say field has its impact to the real system. To the real, sorry, to the real human environment, and it will make the human life better. That's hard to say because we don't have to. So for your own projects, if you want to think using the same structure, start with one clear research question. Write down the assumptions before you start coding. Draw the simple relationship or causal diagram showing what you believe affects what. Create a reproducible baseline. Then introduce one intervention, only one at first. So what you can instant it its effect clearly. Finally, write down what the experiment cannot demonstrate. You do not have to reproduce the smart campus project, because it's I would say, except that you want to use the real data, and it's up to you. It will be very, I would say, honor, or I'll be very happy if you use the I would say the codes that I have in my GitHub. But what I want to say is not an obligation. You can adapt the same idea to your engineering, environmental science, health, education, business, robotics, or another research area that you are interested with. So for our exercises, please continue using the synthetic data or approved low-risk public data. So this is very important. I always mention. So always when we are working with AI, we need always to be careful that the data is not I would say, we cannot play with data. Either with ourselves or with others' data. So we need also always to use synthetic data until validated, until how to say, having the same having the feeling that this data are satisfies our thinking. Then we will use the real data if we can, in local without internet access. So the challenge is to use the many competitions now. They are how to use the real data in offline, so you will not have access to the online AI, and this is very important. So as what up so let's how to say summarize today's main message. A credible simulation study starts with a research question, not with the Python. We define the assumptions clearly and make them visible. We create how to say a reproducible simulation. We verified that the code actually implements the mechanisms we attend. We repeat the experiments rather than trusting one random run using Monte Carlo simulation. And finally, we perform the, how to say, sensitivity analysis before believing the results too strongly. Today, we built the foundation of our smart campus research digital twin. Next week, maybe we'll make this system significantly richer. Instead of using only one sensor and time series data, we introduce multi-model information, image, audio, text, and sensor signals, and investigate how these different sources can be aligned and combined in one research pipeline. This is based on our, how to say, our, I'll be honest here, based on the how to say, the tools that I have, because if we move to more multi-model, there is not problem of the code, it's problem of the resources. The resources, when we move to transformers, to big models, to large models, we need GPUs here. And based on and it's not about the GPU. The GPU, we have the GPUs, but make the model or run big models needs bigger GPUs. That maybe we don't believe that these GPUs are needed. Like I would say, they are doing in Google or in NVIDIA. So this is also based on the time also, because I am preparing the weekly I would say lectures. Not I'm preparing them I would say each week. Is not I have them, or I'm preparing in real time these weeks to make more and more, because if we went, I would say, a few weeks before, the plan that I put is not like that, but to help more, to give more information in the precise and how to say better way. I always change and prepare this in real time and each week. This is also very important to know. Thank you very much, everyone. I hope that today's session gives you some ideas about how simulation can become very practical research tool, especially when real experimentation is expensive, risky, and or simply not yet possible. Thank you all again, and I hope that you learn something today.
Thank you. Are you
Thank
there?
you. Bye-bye. Thank you, Prof. Kim, and I hope that everything is okay. I hope to see you next week, if you, as always, you are.
Okay.
Yeah,
I had a quick question. So
yeah.
your first step on this, like a clear question before any code, like how do you get to that? I mean, here it was, ventilation and, what is the relationship between ventilation, CO2 levels, and comfort? But like, how do you get that kind of clarity?
Yeah, if I because let me ask you a question. I would say, Professor Kim, if you are now, I don't know your room now or your office. You are now in the office. In the
Uh,
office, you are not feeling how to say, and you are not alone. You are with 100 people there. You are meeting with 10 people in your office.
mhm.
So at the first minute, you will not feel anything. You will not feel anything. But after 1 hour, the oxygen, how to say, how to say, it should be consumed. So you will not be in best, how to say, shape. Either you will open the door or you do another thing. So, or increase. You say increase the ventilation. The ventilation, it how to say, brings out the CO2 and introduce the outdoor O2. You will be in that. This is the comfort that we are looking for.
Mhm.
But the idea is not like that only, Professor Kim. The owner of the office, let's say, is not now is Chicago State University. They will not be happy because the energy, it will be consumed more.
Mhm.
If we make all people in comfort zone, means that you will I would say breathe good fresh oxygen, and the reducing the energy consumed for the university, everybody will be happy, and this is the comfort zone. But here I will prioritize you and your colleagues that you are sitting in the meeting, rather than prioritizing the energy. Even though I will consume more energy, little bit more energy, but I will make you in comfort. The baseline, the ventilation is always on, so it always
Mhm.
we have extra oxygen.
Yes, even though nobody's there.
Yeah, that's it. This is the idea. This is now, if you are nobody is there, you will I believe you will, I would say, you will use your how to say your thinking, and you will switch off and go out. But imagine that you are only one, and the
Mhm.
same ventilation when you have 10. This is the idea.
Ah,
So it's
yeah.
not so,
Okay.
based on the number of the people, based on the CO2 sensor, we how to say, it's not manipulate, but control the ventilation to make how to say happy people, happy inside or in comfort zone,
Mhm.
in comfort place, and also without reducing the same energy. This is the idea.
Okay. So it came out of empirical observations, or you know, you know, I don't know. To me, it just seems very hard to come up with a very clear question where your variables are, you know,
No, it's no. Some of the sensors are straightforward.
okay.
The temperature, the humidity, the CO2, and some of them, they are linear system. To be honest, is not, they don't need how to say, the idea itself is important because we are I would say I would say trying to help to the to make the environment good. But honestly, in that time, it was the energy itself. The energy, it was the most important parameter that I was working on. But if you want to let's say, for example, I will give you one example. Let's say the AC that I will tell you, let's close the AC, for example. Can you give us the permission to close the AC for only 1 minute? And multiply this 1 minute by 1 million people, you will have 1 million minutes of electricity consumption. So you reduce 1 million minutes. So, and you don't feel, because switch off the AC for 1 minute and bring it back, you will not feel it at all, because the temperature is I would say is dead, I would say in that time. So the reduction, it will not be the brisk, I would say immediate. So the sensor will measure. So the temperature, when it comes, for example, to 70, it will not immediately switch on the AC until it will go to 71. So, and this is not by seconds; it's by minutes. We compute that. So, the idea is always, if I can say, always. Now the idea is more important than the software or the code itself. This is my thinking now. Make the people happy. The measurements are straightforward. Some measurements are straightforward, but we have other data to simulate to make the sensor realistic. So let's say, for example, we have the real data, and we will have the features of this data and apply to our synthetic data. We will have a digital version of this realistic data, and we will do the same thing. And the ventilation is on I would say PWM control, so it's not a big I would say a big value. Therefore, the is not let's say it's not pH control. pH control is non-linear, highly non-linear. Another, for example, parameter is the compared temperature to humidity and the pH. The temperature and humidity are linear relationship. So the sensor is we are controlling in the linear part, but for the pH is not the same. So when it arrives to neutralization, it moves from basic to acidity or the inverse in a few seconds. So you cannot, even though this is why a lot of people works before on the pH control. It was very difficult topic in that time. But here the system itself is the relationship between the parameters. It's almost linear, and some of them are not non-linear, that we can see, how to say, pick the features from the realistic data.
Okay, so that kind of limits some of the questions that you can even ask, possibly, if you're just
Yes,
looking for simple linear relationships, because not many things in the environment aren't. So, but
true.
this is fascinating, and I have a much better understanding about how digital twins works, because I had often wondered about that. So this is very helpful.
Thanks. This is a good thing. The example itself is not important. The digital twin is the more, how to say,
Mhm.
the most important topic of today. The system is not important. We can have the environment, how to say, or change the system. As I said, you can use it in your research field when you
Mhm.
have more complicated or complex environment system.
Well, this has been very enlightening and helpful, and I'm looking forward to next week, because I mean, seeing all the other sensors added to the model, I don't know, that just seems very complicated. So I'll see how you do this next week.
Maybe I will do that. Maybe I will change based on the system that we have, because as I said when we introduce more data and more inputs like image, audio, and
Mhm.
text, we can have it, but we can 100% we cannot do it in one laptop. Simple
Uh-huh.
laptop CPU. We
Mhm.
need the GPU. But based
Mhm.
on the system itself, maybe we can I will run. I already worked on that before. I will run a few codes, and I hope that we can have it next week. If I don't have, I would say, the possibility to make more data, we can move to another research topic that it will be maybe helpful
Okay.
for the others.
Okay, because I could barely contain all of this. So whatever you choose for next week is excellent.
Thank you very much.